The primary purpose of this video is to illustrate some pitfalls you can bump into when using the combinations formula in conjunction with the multiplication principle. We're looking at a student facing a final semester where what's needed is one math course, one business course, two science courses, but a total of 6 courses altogether, so there's some electives involved here. Here's what you have to choose from. You have 2 available math courses, M1 and M2. You have 2 available business courses, B1 or B2. You've got 3 science courses, S1, S2, and S3. And you've got 4 other courses that can serve as electives. We'll call them E1, E2, E3, and E4. But remember, what you have to have is at least 1 math course, at least 1 business course, and at least 2 science courses. The other 2 courses can come from anywhere. So let's visualize the situation like this. We've got 1 batch of courses consisting of the 2 math courses. We've got another batch of business courses. We've got a batch of science courses. And then we have the electives that we can use if we need to. As a first stab at a solution, let's try this. Let's look at the math courses. We have to take a math course. So let's count the number of ways to pick one of the 2 math courses. And then let's move over to the business courses, where we have to take at least 1 business course. So let's next count the number of ways to pick one of the 2 business courses. Then move over to the science courses. We have to take at least 2 science courses. So let's count the ways we can choose the 2 science courses we're going to take, choosing 2 from the 3. And then after that, we've chosen our required courses. We still have to take 2 other courses. So let's count the ways that we could pick 2 other courses from among the 4 other courses that are available. If we do that, these uses of the combination formula give us a combination of math courses, one of the 2 math courses, 2 ways to pick one of the 2 business courses, 3 ways to pick 2 of the 3 science courses, and 6 ways to pick 2 of the electives. Multiply that all together using the multiplication principle, and you get 72. Now, why is that not the correct answer? Let's think about one specific case that we just counted. It would be the case where we picked M1 as our required math course, B2 as our required business course, S3 and S2 as the required science courses, and E1 and E3 as our electives. And that's a valid case we counted, but you also recognize that there are some cases we missed because, for example, this scenario shows us not choosing B1 as one of our business courses, but we could still use that as an elective if we wanted to. So we could replace either of these electives by B1 or M2 or S1. So there are going to be some examples that don't involve taking 2 of the electives, but rather some more of the math or business or science courses, and we're not counting those. So this is not the correct answer for the question that was posed. Now here's another stab at a solution. Pick our required math course, 1 choice from the 2 math courses. Pick our required business course, choosing 1 from the 2 business courses. Pick our 2 required science courses from the 3 available. And then keep in mind that not only do we have our 4 electives available, but we also still have 1 leftover math course, 1 leftover business course, and 1 leftover science courses. So really, among the 11 courses that are available, we've only selected 4 to meet our requirements. So we still have the other 7 we could choose from for our electives. So instead of having combinations of 4 things choose to, let's think about choosing our electives from those remaining 7 courses. The arithmetic is of course the same up until you get to this last factor, which instead of combinations of 4 things choose to, we'll use combinations of 7 things choose to, since we still have 7 courses to pick from for our electives. Combination 7 things choose to is 21, and this multiplication comes out to be 252, substantially larger count. Let's come up here and look at one of the things that we just counted. That is one of these 252 possible cases. This is the case where we choose M1 to satisfy our math requirement, B2 to satisfy our business requirement, S3 and S2 for our science requirement, and then use E1 and B1 to fill out our 6 courses. So B2 is counting as our required business course, and B1 is counting as a business elective that's being counted as one of our 2 additional courses. But here's another example which illustrates the pitfall we've run into in trying this alternative solution down here. One of the other cases would be the case where we have chosen M1 to meet our math requirement, B1 to meet our business requirement, S3 and S2 to meet our science requirements, and then use E1 and B2 as our electives. The problem is we have counted these as 2 separate cases, but really they're identically the same schedule. Each of them represent the schedule where you're taking M1 from the math classes, B1 and B2 from the business classes, S3 and S2 from the science classes, and E1. So they're exactly the same set of courses. They would represent the same set of courses to be taken, even though we have counted them as 2 separate possibilities when we have used this method down here at the bottom. So we can see now that this second solution isn't correct either. The first solution, 72, undercounted the possibilities, and here we've overcounted the possibilities because we count some cases twice. Let's start over and try visualizing the problem a different way. Let's think of these 11 colored balls. Let's think of the 2 red balls as representing the math courses, the 2 green balls as representing the 2 business courses, the yellow balls represent the 3 science courses, and the 4 blue balls represent the remaining 4 courses. Think about this task, the task of picking 6 balls from that batch of 11 colored balls, and doing it in such a way that we're going to have at least 1 red ball, at least 1 green ball, and at least 2 yellow balls. Take a moment to convince yourself that if we count the ways that this can be done, we're really doing the same math problem as counting the number of ways to plan your final semester, this original scenario that we started looking at. We've reformulated the problem in terms of the colored balls and counting the number of ways to pick 6 meeting these requirements. The way I'm going to look at this is pretty cumbersome. I don't like this solution, but I can't think of an easy solution that works here. What I'm going to do is to break down the problem into cases where each case specifies one way of splitting up the balls by color. So read through these cases and come to understand that this is a complete list of cases. Case 1 is picking 1 red, 1 green, 2 yellows, and 2 blues. That does meet the requirement here. Case 2 would be picking 2 reds, 1 green, 2 yellows, and 1 blue. which of course in the original formulation would correspond to taking 2 math courses, 1 business, 2 science, and then one of the elective courses. Read through these cases and convince yourself that these are all the possibilities in terms of how the balls break down by color. And you'll notice that there will be 2 blue balls, which can occur in this one case here. There are 3 cases where there's 1 blue ball chosen, and there are 3 cases where no blue balls are chosen. But these are completely distinct cases. There's no overlap in these cases, and together they cover all the possibilities. Now, each of these individual cases is actually quite easy. Let's take the first one, for example, which really we've already done. The first case, 1 red, 1 green, 2 yellow, 2 blue, was the same case that we calculated over here on the left. Picking 1 red from the 2 reds can be done in 2 ways. One of the 2 greens, you have 2 choices. 2 of the 3 yellows, combinations of 3 things choosing 2 is 3. And then finally, 2 of the 4 blues, combinations of 4 things choosing 2 is 6. So that gives you 72 with the exact same logic that we used in doing this first failed attempt at answering the whole question. So what we're realizing now is that this first incorrect answer we got was really just one of these cases that make up the entire answer. If you come down to case 2, 2 reds, 1 green, 2 yellows, and 1 blue, we're picking both of the 2 reds. That can be done in only one way. 1 of the 2 greens, 2 possibilities. 2 of the 3 yellows, 3 possibilities. And 1 of the 4 blues, 4 possibilities. Multiply using the multiplication principle, and we get 24 possibilities that give you this case. For the third case, 1 red, 2 green, 2 yellows, and 1 blue, 1 of the 2 reds, 2 ways, both of the 2 greens, 1 way, 2 of the 3 yellows, 3 ways, 1 of the 4 blues, 4 possibilities. Again, 24 for that case. For the fourth case, 1 red and 1 green, 1 of 2 reds, 1 of 2 greens, all 3 yellows, combinations of 3 things choosing 3 is just 1. And then finally 1 of the blues, 4. 16 possibilities in that case. Come down to case 5, 2 reds, 2 greens, 1 way to choose the 2 reds, 1 way to choose the 2 greens, 2 of the 3 yellows, 3 ways, no blues, choosing no things from 4 can be done in just 1 way, the empty set. 3 possibilities there, and similarly you think through the last 2 cases and you get 2 possibilities with 2 reds, 1 green, and 3 yellows, and 2 more with 1 red, 2 green, and 3 yellows. So we've handled each of these 7 cases and counted the number of ways each of those cases can happen. If we total up all of those cases, adding up how many we count in each case, we get a grand total of 143, which should be the correct answer to this question. We had already realized with these 2 incorrect solutions that we started out with, 72 was an undercount and 252 was an overcount because it counted some of the solutions multiple times. So I believe this 143 is a correct approach, which does give us the right answer to the original question. But as I said to start with, the primary value in this example is not so much how you do this rather tedious and complicated problem, but to realize that some of the more simple attempts that you might make are not correct, and to realize why they're not correct. It's a rather subtle point, and there's this, there's having a good understanding of all this depends as much on knowing why simple solutions might be not correct as it depends on knowing how to do more complicated solutions.